Uh, Good afternoon. I'm by names of Katende Roni Magala, and I'm from Group 41. I'll be taking you through quantum feature extraction, and my other partner will be taking as well. Me and my partner, we shall be taking you through quantum feature extraction. Yeah, quantum feature extraction is like a feature within feature technique that specifically is used within quantum machine learning. Before proceeding, let me just take you through a brief discussion between what quantum machine learning means. What I know about quantum machine learning is an emerging field that combines specifically quantum computing and machine learning to solve complex problems more efficiently than any other classical methods. Yeah, this is an emerging field that combines the quantum learning or the quantum computing and involving in the machine learning to solve complex problems more efficient than the classical methods. This quantum machine learning majorly leverages quantum properties such as the superposition and the entanglement and the quantum parallelism to enhance tasks like data classifications, uh, clustering, and optimization. Yeah. So for now, we are doing a project of indoor air quality monitoring. Giving an example, when I want to apply in the QML, which is the quantum machine learning. Here, let me say that we are on a large scale sensor data. We have a large scale sensor data, e.g. the PM 2.5, the carbon dioxide, the VOX, or the humidity. These ones need to be processed quickly. These ones really need to be processed quickly to predict pollution levels. The QML algorithm, like the quantum support machine vector, or like the variational quantum classifiers, yeah, they can be used to classify. They can be used to classify air quality. Yeah, they can be used to classify air quality. Or let me say that if the air is good, then it will display a green. If the air is moderate, like let me say, is there anything affecting the air? Is the air at a poor quality, or like is the air really poor? Based on the real-time sensor data, that's how the quantum machine learning works. Majorly, these models can take advantages of quantum enhanced pattern recognition. Like they can take advantage of enhanced quantum recognition patterns. Yeah. Like for better predictions, let me say that the carbon dioxide, like it rose highly. How was it trending within the previous days or within the previous hours? Like those are the patterns that this quantum machine learning needs to predict the air quality for better predictions. Yeah. Here, going further, let me take you through just the basic introduction. As I've explained about the quantum machine learning. Yeah. Now we are going to the basic introduction of the quantum feature extraction that I'm going to explain today. In quantum computing and quantum machine learning, feature extraction and feature selection. Actually, there are two features, feature extraction and feature selection. These are essential for processing quantum data efficiently. These speed up the leverage quantum properties to enhance computational speed, reducing complexity and improve predictivity performance. They transform raw data into suitable representation for algorithms, improving model performance by reducing dimensionality and removing irrelevant information. So here they transform raw data into suitable representation for algorithms. Like, let me say that we have been having different data, like, that has been collected. It can transform it into graphs. Like, humans majorly prefer reading, like, graphs than numbers, because if I give you a large scale of data, that means that it will take a human being somewhere like over, let me say, like over a day to recognize the highest amount, like the highest percentage of carbon dioxide within any period that had occurred in any period. But using the quantum machine learning, these ones transform the raw data that has been collected within the sensors, or like within the environment, and transform it into a representation for algorithms. Like, let me say that graphs, improving the model performance by reducing dimensionality and removing irrelevant information. Like removing, let me say that carbon dioxide, let me say that we just want what was the highest percentage of carbon dioxide and what was the least percentage. Okay, it will require moderate, because on drawing those graphs, like, we shall see the trend of the movement, but there are some, like, let me say that uh like, it has been like moving, just flowing normally, then that will be unnecessary. Like, we just need the highest percentage at like a percentage where the carbon dioxide has been high, and the percentage where the carbon dioxide has been low. And specifically, like, let me say, in which room, now that is the irrelevant data, in which room has it been, or has it been, like, tested within this area. Okay, this process enhances discriminative power, speeds up training, and increase interpretability. Let me give an example. Now here, in quantum machine learning or feature extraction, yeah, as we are dealing, like, let me say that we are encoding sensor data. Encoding, how do we encode air quality features, like the carbon dioxide, like the humidity? These are encoded into quantum states using the quantum Fourier transform, yeah, the QFT, or the amplitude encoding. Yeah, that's a brief example. Let me say that now the PCA, the quantum principal component, yeah, component analysis. Let me say that this method specifically helps in reduction of the sensor data dimensionality, and while preserving the important features. Yeah, let me say that now we shan't need that. Let me say that we are dealing majorly with the air quality, so we need only features of air quality. We don't know the households, we don't need the prices, we don't anything unrelated to air quality. We just remove it. Like, it will help us to just remove it. That is the principal component analysis, making the real-time air quality prediction more efficient. Yeah, it makes the real-time air quality prediction so much very efficient. Yeah. Going to the importances, like, we have that transforms raw data into suitable representation for learning algorithms. It improves model performance by reducing the dimensionality and removing irrelevant or redundant information. That's what I was talking about the previous. Then enhances discriminative powers of features. Like, let me say that discriminative power of features. Is this feature important? Is this feature really important? Is this feature not important? That is the discriminate in the power of features. If this feature is really important, then it will have the power. Like, it will be valuable, or like within the predictions of air quality. Giving an example via our project, leads to the faster training times, improving generalization and increased interpretability. Feature extraction, now this one leading to faster training times, improving generalization and interpretability. Now, within removing of unwanted data or unwanted data, okay, let me say unwanted features, it will lead to an increased interpretability. Then feature extraction creates new features from original data. Feature selection identifies, actually these importances are, you can find them in the feature extraction and the feature selection. Yeah, thank you. Then the pre-processing step. The pre-processing step here, crucial processing steps in machine learning pipeline. It aims to optimize the feature space for learning algorithms. Proper feature engineering can significantly be able to be used. Then capturing, it can capture relevant patterns, enables models. Yeah. Going further to the techniques, now we have the dimensionality reduction. Here we shall normally use the PCA, the principal component analysis, which extracts lower dimensional representation of high dimensions of high dimensional data, then preserves within the principal component analysis, it preserves important information while reducing the dimensionality, and it identifies the principal components that capture maximum variance in data. Now here I got some application. Let me say that I'm applying it in my IAQ within the indoor air quality monitoring. Now within this, the data set with multiple sensor readings, like let me say that PM10, the PM2.5 carbon dioxide temperature, humidity, the PCA can be used to reduce redundancy. It can be used to reduce redundancy because let me say that we have redundant data. Really, we have redundant data. Let me say that carbon dioxide, redundant data, like the data that repeats itself. Yeah, that's how I understand redundant data, redundancy. Then the PCA extracts most informative features. Let me say now, as I said, we are dealing with air quality. What if we're just dealing with a environment as our domain? Yes, and we didn't pick out the major indoor air quality. Remember, when we are talking about the environment within an household, a household has very many. We can deal with air quality, we can deal with water quality. Now specifically we are dealing with the air quality. That means we shall need most informative features, like we shall deal with the temperature. We need to deal with the temperature. We need to deal with the humidity. We need to deal with the toxic gases, which is the PM10, helping the model to focus on key pollutants that contribute most to air quality verification. Let me give an example. The PCA might show that PM2.5 and VOC levels explain 80% of the variance, while other features contribute less, allowing the model to focus on most relevant factors. Yeah. Then we have the T distribution. Dealing with this T distribution, the TSNE, which can be said which is a distributed stochastic neighbor embedding. Yeah. Visualizes high dimensional data in lower dimensional spaces. Majorly, it presents local structures and separates dissimilar data points, useful for visual clusters and patterns. Let me say that giving an application here, let me give an application whereby we are using it to visualize air quality clusters. Air quality clusters such as good, moderate, is the air good, is the air moderate, is the air poor. It specifically reads the air quality zones based on the sensors, on the sensor readings. Yes, it majorly focuses on those visualizing of the air data, like air quality clusters, good, bad, a good, poor, moderate, and the air quality zones based on the sensor readings. This helps to identify the hidden patterns in the indoor air quality monitoring data by showing how similar the sensor readings, the reading of the clusters are together. Yeah, thank you. So I shall take you further to the domain-specific methods. Domain-specific methods, here we have the male frequency, substroke coefficients, the MFCCS, which extracts features from audio data, capturing spectral characteristics and mimicking human auditory perception, widely used in speech. Now this one is widely used in speech recognition and audio classification tasks. Let me say that someone in there are different sounds. Giving an example, there are different sounds, and now we are going to use the frequency spectral coefficient. Now this one, there are different sounds of let me say that a person crying, a person laughing, and a person who's wondering. So it will be able to differentiate the audio data, like according to the human expression or the human auditory perception. We have the histogram-oriented gradient. This one extracts features from image data. Specifically, it deals with images, capturing local object appearance and shape by counting occurrence of the gradient orientation, effective for object detection and recognition tasks. Now this one, specifically, we deal with image data. Let me say that we are training a machine to identify a tank. Yeah, there are some tanks that are metallic. There are some tanks that are there are some tanks that are plastic, and there are some tanks that are spherical. Sorry, non-spherical. They are in square form. They're in a cylindrical form. So those images that are captured, it extracts features from those images that are captured. And if it captures those, that means it will be able to identify. The feature. Like, let me say that the feature that has been given to it according to the image data that has been already in the data set. Yeah, going further, we have the feature engineering technique. Here, the feature engineering technique, majorly it creates interaction terms to capture relationships between features. It combines temperature. Let me say that an example. It can combine temperature and humidity as an interaction term. Because temperature and humidity, if the temperature is too low, that means the humidity is too high. Yes. Then an interaction term can reveal insights about condensation, effects, and an indoor mold growth potential. Like if we are saying that the temperature is too low, that means, no, let me say that there is warmth. That means the temperature will be too high. That will lead to growth of molds. And if the humidity is too low, that means, like, relating, I hope you understand, like it creates an interaction between the terms. As I've given you an example within our indoor air quality. Now, if the temperature and humidity, if I realize that within the fridge, like the temperature is too high, that means the humidity will be too low. Yeah. Then the general polynomial feature to introduce higher order terms. It will expand feature space by creating new features as powers of original features, captures nonlinear relationship, and increases model complexity. Within this, I can give an example, like how I can apply it in our project. Like, let me say that there is air pollution. Air pollution does not always increase linearly. Like, let me say that the PM 2.5, it may affect the air quality exponentials under certain conditions. Yeah, under certain conditions. Like it can create quadratic pictures. Let me say that the PM2.5 squared, yeah, and can improve the model accuracy. Hope now giving an example, like the PM2.5 squared has a stronger correlation with bad air quality than the PM2.5 alone. If you multiply, like if you keep on multiplying, that means it has a stronger correlation with the bad air quality than the let me say that than the original one alone. Like it leads to the polynomial expansion, which helps to capture this effect. Yeah. Thank you very much. I'll end there and allow my another presenter to present. Thank you very much.